and the traffic and the one lane on Broadway. I want to welcome everyone today. It is my pleasure to kick this off. My name is Christine Wiedemeyer. I'm the Associate Director for Science at Series. Unfortunately, Anna Gold, who is the Director of Education and Outreach, is unavailable, so I get her job today. So you can pretend like I'm as good as Anna. First of all, for those who don't know, RECCS, or the Research Experiences for Community College Students, is nationally funded by the National Science Foundation. It's a research experience for undergraduates. These REU programs go on all around the country. This one is, I think, especially successful. It's run by Series, and it's also partially funded and run through the National Science Foundation's Critical Zone Observatory, or CZO, thanks to Suzanne Anderson and that program. And that really, I want to thank a lot of our sponsors, the National Science Foundation, Suzanne, and CZO. I really want to thank all of the mentors, the faculty, the scientists that have mentored the students this summer, as well as all the graduate students, because I know a lot of students come in to work with research groups, and it's not only the scientific leaders of those groups, but also all of the staff and scientists that are working with students that are really mentoring and helping out with these projects. So thank you. I want to thank Jenny Briggs. She's been instrumental in this program this summer and running the science communication workshop. Renee Curry-Minea, did I pronounce that right, Minea? So Renee, just so you know, Renee just started in her position in May. She came in and really ran this program this summer. She's done a phenomenal job. I know Anna completely appreciates it. Amanda Morton for logistical support. Where's Amanda? What? Oh, she just ran outside. I can thank Amanda when she comes back. And Katie Weeman from Series Communications, really for supporting and the filming and the communications. Just a few facts about RECCS before I move forward. This is the 5th RECCS cohort. So the 5th year that we've done this. The program is well recognized by our sponsors, and that's why it's continued to go on. We've had 11 students this summer. 4 students worked with scientists over at the National Oceanic and Atmospheric Administration. 6 students worked with fellows or scientists associated with Series, the Cooperative Institute for Research in Environmental Sciences, and 1 person worked in the geology department with Eric Small there. Again, this activity right now is part of 2 deliverables that the students had to accomplish by the end of the summer. Yesterday was the poster session. I was able to go for a little bit. It was outstanding. I was very impressed. I hope you enjoyed yourselves. It was great. And then the presentations today. Anna just wanted me to know, there's been a lot of growth of the students who participated this summer. You all have worked extremely hard. She's been nothing but impressed, and particularly with the perseverance and dedication that you put into your projects this summer. One of the eye-opening things of coming and doing research projects is learning that not everything works properly, not everything goes as planned, and there was a lot of dedication and perseverance in the group this summer to make sure that they had valuable results by the end of the summer. And then I also wanted to mention, as you move forward from this program, stay in touch with your mentors, stay in touch with those you've worked with, stay in touch with your cohort. They can be valuable assets moving on. This is, a community that you formed, and it's not over when you leave here today. So I'll hand it off to Jenny. Oh, you just got to say and thank you all for having me. I'm looking forward to your talks.
Yeah, so I'm Renee Curry-Minea, and then Jenny's going to follow me, and then we'll get started on that. So I'll have just a couple of words, and I'll move on to Jenny. Like Christine said, I started in May, actually half-time, and I want to give credit to the founders of the program, which is obviously not me. It would be Anna Gold and Leslie Smith. So Leslie Smith was the one in my position before I came in May, and she really was the one that selected the students and paired with the mentors. I really give her credit for that. And she came to the poster session yesterday and had a really great time judging and used her camera. It was all really nice community building, I thought, yesterday. So Anna's really bummed she couldn't be here. She's home in Germany for a very special occasion, and so Anna's been great to work with and helping me out a ton as I'm having a learning curve as I'm going along. And that being said, Jenny Briggs, I'll give you some accolades too before you go. She was really our science communication lead for the summer. So every week, every Wednesday, half a day or a little bit more, we would meet with the students on working on deliverables for some of the projects here, the poster yesterday and the oral presentation today, as well as in like blogging and other types of style of communication, like elevator speeches. So it's really fun working with them and learning about the array of projects that's been going on between, I would say, CU series, and that was an amazing to see for me. As well, I want to thank Amanda's running around like normal for her, but we have an amazing rec support staff that's been really helping me this summer, and the students in the front, thank you for all your help as well. They're helping me out a lot this week in particular. So thanks for the last minute help on that. And I think for me, like, I was so floored in a really positive way of yesterday. The judges, every single one was like, they were so good. They only had 8 weeks to do research, and I was like, I know, right? And so they were really, really impressed by everyone's presentation, and those that had challenges really rallied. And so we're really, really impressed by all of you, and we're so excited that you had that confidence boost yesterday and had some time to talk about it and things like that. So we're going to have this presentation for you guys today, which you're going to rock, and then we're going to have a fun cupcake reception afterwards. All of you are welcome to join us for in the next door over here. So that's how many things I have for me, so I can give it over to Jenny, and then she'll get started.
All right, well, welcome everybody again. This is a great turnout, and my role here is to thank not only the students for your incredible hard work and perseverance, but again, the mentors. I was a mentor in the second year of this program myself, and I know what a lot of time and energy it takes to build a project with a student. And a lot of you gave new projects and pilot studies to your students to take on, and that's quite an adventure, as we've all found out. So thanks again to the mentors and for keeping in touch with all of us. But I also see family and friends here, and I want to recognize and give a shout out to just community college students and family and friends in general. I attended a community college myself long ago, and I know that I was juggling jobs and family and all kinds of responsibilities at the time, and I needed a lot of support from my team to put education into the picture as well. So thanks to everyone for all the support that you've given to our 11 students this summer as they did this intensive kind of full body immersion into the world of research and science at CU Boulder and federal agencies and all of that good stuff. As we've said, the outcomes have been really amazing. And some of the judges to me said yesterday, are you sure these are not students who actually have advanced degrees from other places or extensive training and preparation? Because they felt the quality of your work and your presentations was really outstanding. So, so not to build everything up, we know, we know that presentations can have their own surprises, but I know you'll all get a flavor for each project today. And then when we, after the wrap up at around 3:10, or possibly precisely 3:10, I will do a quick sort of acknowledgement to many of the unique qualities of each student's work. So if you can stick around for that, that's something that we'll add in before we go and have cupcakes. It should only take about 5 minutes, but we have a little recognition for each student and for the mentors too. So with that, we will get to our first presenter. Thanks to, there's always someone who has to go first today. Thank you, it's Cora Rutledge. And Cora has worked with Melanie Shudor and Noah Fearer. And apologies in advance if any of us don't pronounce anybody's name correctly, please correct us later. But we will, yeah, I'll get it.
And reminding to our students for audio, we're live streaming this as well, so make sure you prepare.
Thank you.
Alright, so this summer I studied the effect of volatile organic compounds, or VOCs, emitted from compost on soil microbes. So do me a favor, close your eyes if you want to, and imagine the smell of a freshly composted garden after it's just rained. Most of what you're smelling saplings are made up of volatile organic compounds, or VOCs. These are small molecules that are easily vaporized at room temperature and often have a distinct odor. A diverse amount of VOCs are produced by bacteria and fungi, and these bacteria and fungi often come from plant litter and compost. So we chose compost to study the emission of VOCs. So now there's been a lot of studies done on how VOCs specifically mediate microbial interactions, but not a lot of studies on how these VOCs affect microbial growth rate and abundance. So for this question, we've got a couple of hypotheses. First off, we predict that compost VOCs increase the growth rate of soil microbes, and for a couple of reasons. They could provide nutrients to these microbes, or they could signal the germination of the microbes. An alternate hypothesis to this is that they actually decrease the growth rate, and that is because there are some VOCs that are known antimicrobials. So in order to test this hypothesis, we took 3 types of compost. We've got mushroom, sheep and peat, and garden compost. We've also got 4 soil types in 4 different locations, including agricultural, tropical, subalpine, and a lawn from my very own Boulder, Colorado. Now from each of these soils, we took 1 gram and we put it into a buffer solution. We put those 4 soils onto different petri dishes into a nutrient-rich powder. And then we put those petri dishes inside of a jar on top of compost. There was 5 to 6 replicants of each soil. And then for the compost, there was 1 of the 3 composts or a no compost control. We wetted the compost to 35 to 50% water holding capacity, which is the maximum respiration rate for VOCs. We put all these jars in an incubator at 30 degrees C for about 5 to 7 days. And then we looked at the petri dishes. Specifically, we counted the colony-forming units, which if you look at the petri dishes, each little dot represents 1 colony-forming unit. We count all the colony-forming units for 1 plate, count the abundance, find the midpoint, and we graph them on these box plots. So at the bottom, on the x-axis, you can see there's mushroom, sheep, and peat garden, and then the no compost controls, which were not exposed to VOCs. Those are highlighted in purple. The y-axis represents the colony-forming units for the 1 gram of soil, and those are in units per 1,000. So if you can look at the subalpine, the most CFUs that it produced was 250, but that's actually 250,000 CFUs that it produced. To give you an idea of the vast differences of these different soils and their production, the most CFUs that the agricultural soil produced was actually 15 million. So if you'd like to look at the different soils and just like take it in and how very different they are, and also look at how differently they all responded to the different composts. So we took all of these composts and put them together in 1 count, and then we did a t-test between the ones that were exposed to VOCs and the ones that were not, in purple. And then the top 2, the agricultural and the local lawn, are the ones that had the significant p-values, while the bottom ones did not. I would like you to look at the tropical though, even though it didn't have a significant p-value. It does look like more CFUs grew in the no compost control than the ones that were exposed to VOCs. So this next graph kind of shows the significant, the 2 soils that have the significant p-values with all the composts together. So you can kind of get a good look at how all of the compost had more CFUs than the ones that were in the control. So what does all of this mean? Well, it means that 2 of our soil types out of the 4 actually had an increase in the growth rate of soil microbes. This means that it proved our initial hypothesis. But because the soil types were so different, it also means that just generally we found that VOCs influence the growth rate of the soil microbes. This influence is highly dependent on the type of compost that's chosen and the type of soil that is studied. In the future, we would like to look at specifically what VOCs are emitted from the compost, as well as what microbes are grown on the plates. So this last one would be really interesting if we could identify them with molecular biology, because when we take soil from outside, we give it food, nutrient-rich agar, we give it a good temperature, 30 degrees C, we can only grow a small amount of the microbes that are actually found in the environment. So we could potentially look at, do VOCs influence growth of microbes that we've never seen before, and be able to study that in the future. So, these are my references. I would like to give a thank you to Mallory Shador, Noah Theater, and the entire Theater Lab for their contribution and guidance in the entirety of this project. I would also like to thank the RECCS program, and they are funded by the National Science Foundation.
So we'd love to have questions for Cora and for each of our speakers. And something that I forgot to say is I've emphasized to the students that scientists ask a lot of questions, and all audiences do. And scientists' questions and audience members' questions are always extremely positive and geared towards improving future work and understanding more about the study that was done. So in that spirit, you can ask Cora anything you like, and I'm sure she'll be happy to give it a try.
So when you showed the petri dishes, there were different colors to the dots. What does that mean?
Yeah, so if you look at this petri dish, the different colors are actually different microbes. And we didn't actually analyze their DNA, but we can see just by looking that they're like, this is a different type of, or species of microbe than this guy.
And then between the different soils, did you have differences in the colors, or did you look at that at all?
Yeah, so the colony morphology of each of the soils was actually really different. So this guy is from subalpine, but then there were plates from the tropical soils that had bunches of very tiny red microbes just strewn throughout the plate. And so the types of microbes that we found, at least in qualitatively, were actually very different. Yeah.
Where did you get the tropical soil? Was that something you bought somewhere, or is it actually from the project?
So it's actually from Panama, and I didn't have the funding to go to Panama. My lab actually was already using that soil for a different study, and so I was able to use that. I did collect the one from Boulder, Colorado. Yeah.
Is it actually a good thing for microbes to grow in soil? Is it something you want? Or?
Yeah, well, microbes naturally grow in soil, and so it's something that could influence the growth of plants. I mean, it works together in the ecosystem, so they're actually good.
So VOCs are basically, that's what makes something stinky, right?
Yeah, and in some respects, not all VOCs have odors, but yeah.
Okay. And so within your experiment, how did you know, is there any sort of independent measure of how much VOC was within the?
We didn't have a specific measure for that. We just knew that they would be emitted from the compost based on previous studies, but I mean, when I cleaned out the jar, the compost was pretty smelly, so that could be an indication.
Cool. Can you describe the process used to count all of these zillions of colony forming units?
Yeah, so we took one of these plates and we diluted it down to get about 30 to 300 colonies per dish, but then we back calculated to find out how many microbes are actually in the 1 gram of soil. That's why they were so different. So really I was only counting about 300 to 400 per plate, but then in the back calculation you can kind of see how different the microbe count was. Yeah.
Did you compare dry versus wet soil at all?
We didn't, not for this one, just because we wanted them all to kind of be in the maximum VOC respirations. Yeah.
All right, let's give another.
Sorry, that was my fault. How was this
Then everyone really speak up when you're up there so that people can
Are we
hear.
good now?
Yeah, I moved a little
Thanks
closer.
for
so
going first for figuring out the
Sorry about my shuffling during that last one.
Alright, so I'm going to introduce Davin. Okay, so the next speaker is Davin Duke, and his mentors are Jenny Berry, and Eleanor Ellie Brown, the CU Chemistry Department within Series. And I will let him take it over. It's all you, Davin.
Yeah, so I've been working on a new approach to measuring nitrogen deposition in Rocky Mountain National Park. And before I get started, I just want to say thanks to the group I've been working with in the Brown Lab They've been really helpful and really smart, and I really appreciate it. It's been fun working with them, and just being here at RECCS and series, and just having the NSF grant to fund me to do this has been really fun. And so our main motivation behind finding a new approach to finding nitrogen deposition in Rocky Mountain National Park is because excess nitrogen pollutants are degrading the grandeur of our backyard. A couple of the ecosystems in Rocky Mountain National Park have changed from nitrogen limited, which is normal. Nitrogen is good for our ecosystems, but with the excess deposition, they're changed to nitrogen saturated. You can see in the top left picture with the leaf, that is a leaf going under chlorosis of foliage, just the yellowing of leaves. That's when the chloroplasts start to break down because of excess nitrogen. Makes for a bad salad. On top of that, it's just mainly reactive nitrogen is causing these issues. And then I have a picture here of algae blooming in Lockvale as a location in Rocky Mountain National Park. So before we even showed up to the picture, the Nitrogen Deposition Reduction Plan, NDRP, has already been measuring nitrogen deposition in Rocky Mountain National Park. You can see that due to policy changes because of the plan, that they've decided that the blue line, the glide path, should be the expected amount of nitrogen deposition in Rocky Mountain National Park. However, you can see that with the wet deposition rolling average in red, we're still well above that. With that being said, you can see this was published in 2017. The last data point is from 2015. So you can see that wet deposition takes a long time to process, and it's also very expensive. So we've been looking at alternate methods to measure deposition. So I've been working on a sampler that will enable us to measure not only some of the wet deposition that they're measuring, but also another 30% of it that we don't know a lot about. Nitrogen compounds are very complex and at low concentrations, and there's little known about it. So with this sampler, it's no bigger than the size of a pen. It's just a 1/4-inch diameter glass tubing containing an absorbent bed of either 10X or charcoal. This one shows a picture of charcoal, and what an absorbent does, it just absorbs the compounds onto the surface of the matrix, and it kind of just sticks to it. On top of the sampler design, these are very cheap and a lot easier to use than the process for wet deposition measurements. And we could just bring this SIMS up here. It's called a chemical ionization mass spectrometer, more specifically high resolution time of flight chemical ionization mass spectrometer. And we could just take this up to the mountains, but it's very heavy, very expensive equipment. And with the SIMS being paired with the samplers will be kind of part that's just grabbing the air, and we'll bring it down and measure it with our chemical ionization mass spectrometer. What it measures is mass to charge ratios, and that's how we're able to indirectly identify each compound that's coming off of the samplers. How we get the compounds off the samplers is through sampler conditioning. We call it thermal desorption, and the technique is used to clean the sampler and get background, and it's used throughout the whole process. You see in the red circle that we have the sampler. It's wrapped up with insulation, heat tape, and a temperature probe. As we're heating it up, gas flows from the right side of the picture to the left side into the SIMS, and that's just kind of the process of what it looks like when we're doing thermal desorption. And so the results of thermal desorption, we were trying to, this is a trace of trimethylamine. Here's just a quick picture of the compound, what it looks like. But to orient you to my graphs, on the bottom we have the time of the thermal desorption, and on the left, on the y-axis, we have the signals that the SIMS reads us. Pretty much at higher signals, we're getting higher concentrations of that compound coming off the sampler. So you see in thermal desorption 1, signals get very high. With the grayscale increasing with temperature, with higher temperatures, we saw greater concentration coming off. And in thermal desorption 2, it looks like this is what the background should look like for us. And you can see the peak has gone down a lot, and now with the lower signals, we're able to see differences. With that cleaning and the conditioning done, we moved on to a control test in which we could relate a signal with a concentration. This is just a quick diagram of the control test, and we were measuring trimethylamine specifically. And on the left there, we created a target analyte solution. It gets heated up in the heating tube. The gas gets diluted into atmospheric concentrations, flows through the sampler chamber where we mimic passive sampling, which is just what would we be doing actually in Rocky Mountain National Park with the spontaneous diffusive air through the sampler. So TMA, trimethylamine, after the control test, you recognize the thermal disruption 1 and 2 again. And what we expected to see is to go from the signal we see in the first thermal disruption to the second and then back to the first. We wanted to increase the signal again. But from here to here, the signal went down. And what this shows us is that we need to do the control test for longer, and that way we'll be able to see actually differences in the signal. And we would also want to thermally distort to this level instead of just starting at that level, so we can actually see these differences. That is kind of the progress to date. We've moved on to just do a quick outdoor sampling between the two different absorbents I was talking about, 10X and charcoal. You see in the circles here, that's the actual samplers. Again, just the size of a pen. I taped them to the outside of our lab window over the weekend, and yeah, you can see lots of tape. Didn't want those to fall. And so this is just a quick comparison of what the background was reading for 10X and charcoal, and what the outdoor signals we received. And you can see for ammonia being an inorganic nitrogen, which we can also see in wet deposition. It's just cool that we can see the same measurements that they could take with the wet deposition measurements from the nitrogen deposition reduction plan. However, you just see the increase of signals on both the outdoor. So it was great to see that we were able to see a difference between the outdoor. So it shows a little bit of use with the sampler. This is just a little bit of a relationship that we can see. The mass to charge ratio of 110 is a mass to charge ratio related to ammonia, and it shows that 10X and charcoal both increased with these. However, if we go down to the blue, only 10X increased with the signal mass charge of 151, and charcoal decreased. So they did opposite things. So it just shows a little bit of relationship of what the absorbents can do. On top of that, it just shows possible formulas and possible identifications. And with that, we would just make calibration curves to relate the signal, and that makes we're able to make quantitative measurements. And we put them everywhere in the Rocky Mountain National Park, and actually be able to get down with the calibration curves. We can start making policy changes eventually.
Thanks, Gavin. Thank you. We have time for a couple questions from the audience for Gavin. Go ahead, Rick.
Oh, hey, sorry.
So when your plots are showing time versus signal?
Yeah.
So this is, just so I understand it, so this is in the lab?
Yes.
Then, and so the actual specific time doesn't really matter. It's the length of time after you start boiling this stuff off of your
pretty much, yeah.
Charcoal sponge, right?
Yeah, so if we were to, like over the weekend, you saw the signals actually increased as opposed to our control test. The control test was only run for about 2 hours versus 48 hours on the weekend. So we now know that after we clean it more and run the test for longer, we'll be able to see differences in the signals.
So do you think you're picking up different compounds, like some come off easily at the beginning, and then as you run the test longer, you're getting other types of
not necessarily. I specifically showed just the one plot for that signal. We were measuring mass to charge ratios from 200 and below to 7. And so that was the one specific related to ammonia of 110. And so it was kind of just showing that with increasing time of doing thermal absorption and increasing the temperature, kind of just relating that as we heat it up, give it more energy, it will be able to come off at that temperature. We went up to 300 degrees Celsius.
And then you don't reuse the charcoal, right?
Yes, we do reuse it. We would just clean it again.
One more, go ahead.
Less a question, more of a comment, which I know we're not supposed
Okay.
to do. But I think it would have been awesome if you'd put some samplers in Cora's jars.
Yeah, they could work together.
If there's one argument for utility of compost, is that it's these volatile nitrogen compounds that may be fueling the soil.
Mm-hmm.
So,
Yeah.
anyway, it's not really.
No, that would work together. Yeah.
So one more in the back, we're going to move on. Go ahead, Nisha.
Do you know what is causing excess nitrogen to be deposited in that conventional site?
Yeah. So primarily from anthropogenic sources, so human sources, cars, byproducts, and feedlots, and that's what the policies from state and federal laws try to change, so that they aren't, releasing these excess nitrogen as often as possible.
From atmospheric pollution?
Yeah, so it just goes in the air and makes its way up, especially at higher elevations is where it's causing more damage in the mountains.
Great. Thank you, Gavin.
Thank you.
don't want to trip anyone, but this needs to be close for people to hear.
Is it not quite close enough stuff?
Well, no, this works, but I'm going to be blocking people. Yeah, that might be the best option, actually. To avoid tripping and also the camera.
So our next speaker is going to be Sean Will. When it shows up, we'll see what he's going to talk about. Michigan's beavers. So Sean's mentors, we're going to go ahead. Sean's mentors are Emily Fairfax, and then Eric Small from the Department of CU Geological Sciences. And I'll let Sean talk about his projects. Go ahead.
Hello, so my project this summer was studying the hydraulic conductivity of beaver dams and of beaver pond soils, and the hydraulic conductivity being the rate of movement of the water through these soils. So what are the beavers doing in these ecosystems? They're cutting down trees and they're building dams. It's really simple, but it's the effects of those that the simplicity ends, because by removing the trees, they're removing tree cover, they're removing a canopy. By doing that, they're allowing other species to grow that otherwise wouldn't have the opportunity. They're also putting away lots of water in these basically natural freshwater reservoirs. Our objectives was to determine the permeability or the conductivity, of beaver habitat soils. So we wanted to see how they flow through various sites in various different dams and ponds. We also then wanted to compare the conductivity of a pond to its dam to see if there's some correlation there. And we wanted to preserve the soil samples that we took for future analysis. Why is this important? Why do we even care? It's all about the fresh water. Beavers cause the water tables to rise when they build these natural reservoirs here. Their ponds don't just contain the surface water that you see and you can visualize. It also begins integrating itself into the groundwater. And that's what we're trying to find out, is get a more accurate measurement of exactly how much water these are holding in their ecosystems. On top of that, they allow a large body of fresh water for native wildlife to access without having to worry about competition, and provide still fresh waters for native amphibian and fish species for spawn. So, methods. We went out to a number of locations here very close to Denver. The two sites there on the map were just south of Breckenridge, and Left Hand Creek is only about a 30-minute drive from this location here. We went out there and collected soil samples from various locations within the pond themselves, against the dams, and just had a good time doing it. We then took the samples and ran them through a permeameter. This permeameter is what is used to measure the conductivity. What it does is it simulates a hydraulic gradient by putting pressure on these vials of water here and then running it through these tubes into a sample canister of water or of soil. So by gauging the hydraulic gradient and then calculating that alongside the size of the sample and the volume of water that's flowing out over time, we can calculate K, which is hydraulic gradient. So what we found was, it turns out that the beaver dams consistently had higher conductivity rates than their corresponding ponds. That was a surprise to us. We expected that the beavers would actually be choosing less conductive soils, soil where water doesn't want to flow through, because they want to make their dams more waterproof. If anything, though, if it was going to be different from that, we expected them to be more similar, since the mud that they use in these dams come from the ponds themselves. So the fact that these are actually much higher shows that the water wants to flow through the dam soils more than it wants to flow through the pond soils. And I'm curious, and worth another look. But we can do better than graphs. We can actually go ahead and apply this to the Hydrus 2D 3D model. This is software that allows us to model visually how water is moving through soils and at what rate. So we can put that up here and start seeing how the water is flowing into the groundwater and through the dams. So from here, for future techniques, we want to standardize the sampling techniques. We want to have more regularity in where in the ponds in relation to the dams we are taking these samples. We also want more data points. The problem with that is simply time. It takes a full day of lab work to run between 2 to 4 soil samples alone. So to help with that, we're also preserving soil samples, as I mentioned earlier, and we're going to determine the physical composition of these soils to see both the grain size distribution and the amount of bulk organic material like wood chips that the beavers leave behind when they're eating, or pine needles, and see how that affects the conductivity. Because if we can better model how these soil samples affect that, we could potentially come up with field measurement techniques that allow us to go ahead and test these in real time in the field and not have to worry about days at a time in the lab. So that was my talk. Sorry for the acknowledgements. Thank you very much.
Questions from the audience? How about?
Yes.
Go for it. Either one. Here we go.
And maybe I misheard you. I think you said that you expected that there would be a preference for less permeable soils from the beavers themselves.
Yes.
Have you? I know you had limited time for your research, but is there some thought as to sort of comparing beaver dams to sort of naturally occurring log jams that have created some sort of ponding ammonia?
Not during this research, but that could be a focus for further research into why this exists, as to why this difference exists. Also, collecting more data points could point to this being more of a anomaly. It doesn't seem that way since we were taking from different ponds and different sites, but that's also a possibility we'll see with more data.
So just so I understand, when you say pond soils, are you talking about the mixture of mud and sticks that they pack in to try and
Yes.
fill in the gaps?
Yes, the soils that are in these beaver ponds, they are not just the sediment that washes there into the soil from the stream system. It is also the when they chew down their trees, they leave a lot of wood chippings behind, and they also then form those logs into preferential standards for their dams. They fit it together. And all of this over time leaves a lot of organic matter in those soils that wouldn't otherwise be there if it was just the free running stream. So that's going to change the composition, the dynamics, and we need to better model that.
Another question? There's one or two. What is involved with the sampling? Do you just like take a trowel and dump soil in a Ziploc, or do you like take little pores and then?
That's actually not far from the truth for some of the samples I got from my mentor. But most of these samples, like when we were out here, from the middle of the pond, we have a large iron auger that we use to just pour out small samples of soil from the bottom of the ponds. And yeah, from the dams themselves, it's usually just a trowel, so we can reach down there and carefully take away that sediment. And yeah, it's just a matter of keeping them in Tupperware. So. Yep.
Did you ever find any angry beavers while you were like?
We saw no beavers. At no point did I see a beaver through this entire study. Basically, every other bit of wildlife in Colorado.
What was the big wildlife that you saw?
Moose.
Very cool. So I think we're actually going to move on if that's okay. So thank you, Sean, for that. Give it away. The next speaker is Jessica, we call her Jess, Gent, and her mentors are Katie Barnhart and Greg Tucker with the CU Geological Sciences. So they talk about your project, Jess.
Hi, so my research is the impact of ground control points on drone-based structure for motion. And we're actually going to start off by talking about debris flows. So, yes, so debris flows are really just more of a technical term for what you would think of as a mudslide. This big surge of water and rock and sediment, and they can be very dangerous, so it's really important that we learn more about them. And we've actually got a really active debris flow site right in Colorado. It's called the Chalk Cliffs, and we've got pictures of that right up here. So Colorado, yes, has this debris flow site, and it's on Mount Princeton near Buena Vista. which is a couple of miles or a couple hours southwest of Denver. So ultimately, our team's long-term goal is really to understand more about how debris flows initiate. And in order to do this, we've been making digital elevation models of the cliffs and comparing them over time to see, how are things changing. But in order to make these models, we need to collect data at the cliffs. So, what is the best way to go about collecting this data? If you were thinking LiDAR, pretty reliable method, well, it's actually not really feasible here. It's not only is it really expensive, but especially terrestrial LiDAR is just pretty much impossible at the chalk cliffs. The terrain is really rugged, it's very steep, it's loose, it's kind of dangerous to go into. So we actually use instead this cutting edge technology called drone-based structure for motion. And structure for motion is really just this process of using a moving sensor that our drone's camera. We're collecting 2D images and we're making something three-dimensional out of it, and we're giving structure to it. But we don't need any location data to make a model like this. We just need a really good set of pictures. So this is where our ground control points come into play. And you can see one here on the ridge on the cliffs. And it's really just about 1.5 feet on each side. And it's this physical marker that we know the GPS location of. And it becomes really critical to measuring topography changes. So we actually have 15 of these out on the cliffs. And this is the chalk cliffs. And you can see the names and locations of all of these. And ideally, we would like to have more out there, but just because it's so difficult to put equipment out there, it's worth exploring how effectively we can use what we already have. So previous studies by Nadine Raymond, who has been here actually, previous studies have looked at this relationship between the number and the distribution of points we use and how this impacts our model's error in meters. So you can see as we increase the number of GCPs, eventually our error plateaus and we don't really need any more. So that's what my research has been this summer is, can we minimize the number of control points we need in really rugged terrain? And then, by proxy, we're also kind of asking, can we even use this type of method, this drone-based structure for motion, in this really difficult terrain because it hasn't really been explored before? So the first step of this is all the fun field work you get to do. So 4 times throughout the summer, we went up to the chalk cliffs and we used a Phantom 4 Pro drone, which anybody could buy. And you can see it taking off here. And we collected about 900 images on each flight. But, what do we do with those images after? So this brings us to our processing stage. And we use this modeling program called Agisoft PhotoScan. And you can see these are what the pictures actually look like in the drones. And we have to kind of spot these little ground control points in there. So we go through this process of tying together our images and marking all of these control points in our photos to get our location established. And after that comes the most important part of this, which is, how do we go about exploring that number and distribution relationship? So how I went about doing this is actually making 15 different models. So in regards to exploring the number, I created different points with 3, 6, 7, 8, and 9 points. And then within those, I made 3 different combinations focusing on either the channel or the entire basin or the ridge where these flows initiate from. And something important to note here as well is that this is not a plot of results. If you look at this figure that we showed before, these grids are actually just these locations. It's just where the locations are of each point relative to each other. And the differences in color just represents whether I used it to make the model or not. So these darker points are the ones that I chose to make the model with. And the lighter points, those are just called checkpoints. And all those are is all of the other points that I didn't use. But we still know the location of those, so we actually use those to measure how accurate our model is. So this checkpoint error plays a big role in our results later. And then after that, we just ran a series of error reductions called gradual selection. And really all this does is just kind of pulls out bad pixels that we don't want in our images. So as a reminder, what did we expect? So we were hoping that as we add more ground control points on, our error will be reduced. So I'll bring in our results slowly. And you can see that with only 3 control points, we're still getting errors of 4 to 6 centimeters, which, I'll remind you, it's a commercial drone anyone could buy, and we're flying it 400 feet above the ground, so that's really good in such a complicated area. So then we bring in our 6 control points. This is great. We've got that downward trend that we were hoping for. So what happens when we bring in our 7 to 9 points? Not what we expected. So clearly something went wrong here. I can get into that in the question section if you are interested in what happened there. But to kind of wrap up what the most important takeaways are from this, you can see here that, I mean, we answered our question. We proved that drone-based structure from motion is an effective tool in rugged terrain because we were able to prove that by cutting our control points by more than half, only down to 6 points, we were able to get an error of only 4 centimeters in our model. And we're measuring stuff that's happening on a scale of meters. These debris flows are eroding and depositing sediment in meters at a time. So 4 centimeters of accuracy, that works, that gets the job done. And then, the last kind of takeaway point is that really if we want to answer our question fully and see, what this trend does, if 6 is really if that's the point where it plateaus, or if, we really need more points than that, we're going to need to put more equipment in the basin so that we can extend our data set. So I'd like to thank everybody so much that was involved in this project and this experience. It's been a wonderful summer. Also, thank you to the National Science Foundation, and I'd be happy to take any questions now. Thank you.
Time for some questions. Go ahead, Joe.
Yeah, so how did more control points actually cause that weird result?
Yeah, well, so I've got slides for that, so I'm glad you asked. So it turned out, so I mentioned that the checkpoints become, what we use to assess the model's error. And you can see that as we add control points, and because we have only an established number of points to pick from, so as we add more control points, we're taking away checkpoints. And it turned out that there was one particular point in all of these that are highlighted that had a higher error value than most. And so as we took away more control points, like its error impact kind of became less diluted, so it threw up all of these other.
Is there a way to identify an ideal number of control points then?
Oh, well, I mean, so we were able to determine that 6 would work for what we're using it for, but that's why I was saying we would need to put out more equipment in the basin just to be used as checkpoints so that we can use more control points and see what that trend looks like when we continue.
Go ahead.
So what time resolution do you see this being used for? Like, do you imagine it being used for like mudslides that are happening on like a second? Do you think you could use that? Do you see that in the future of this?
To measure the flows, you mean?
Right. So like, if you're using this method to measure like debris flows, like what time resolution do you think that?
Oh, sure. Well, we've actually, so we do flights out there every 2 weeks, which is one of the benefits of having this so close to where we're located. And we've already noticed changes in there. We haven't been able to georeference all of the flights we've done yet, but we've made preliminary models, and we've already determined that there are changes happening. And I actually had discovered throughout this process, there was a point that I had used in some of my combinations, and I had to take it out and rerun it because I discovered that it moved in a debris flow. So we are able to pick up changes from between even just individual flights that were out there.
Oh, well, there
are.
Okay.
Yeah, mine too.
Okay, well then 2 down, you're next.
So I guess my question would be like, so this is on the debris flows occurring in that region. Like, how applicable is this to other kinds of debris flows that are made of different types of materials going at like different rates?
That's a really good question, and one that I'm honestly not 100% sure of the answer on. But really, the focus of my part of this research was to see, is this an effective method in this kind of really difficult terrain? So I'm sure that there's a lot of future studies that could benefit from this, and even if the more nitpicky aspects of how debris flows initiate are different there, I'm sure that it would be useful there as well.
Okay. Well, thank you. Thanks, Jess. Okay, keep doing that. Give away the end. So our next speaker is Joseph Brown. I'm gonna get this right. His mentors, his mentors are Milen Jacquemart and Christine Zopek, and then Christy Tiampo from CO Geological Sciences in series. So take it away, Joe.
All right, so I'm Joseph Brown, here to talk about single landslide. You see a nice beautiful picture of it right here. This is the actual landslide going down. So some blue landslide is actually located here in Colorado, the western slope, close to
Keep going. He's bouncing on me.
just outside of Lake City, Colorado. Initially, the first actual landslide occurred about 700 years ago, and then approximately 350 years after that, we had another landslide event that took place. And since that second landslide event took place, it's been moving at approximately 1 to 2 centimeters per day, which I think the total average is about 7 to 9 meters per year. So the beauty in this is that it actually gives scientists and researchers the capability to go research landslide kinematics. And so that's kind of what we did. And so many scientists refer to it as like a natural laboratory because of what I just said. Gives you the option to go study it. It's not dangerous. It's moving so slowly. So when I first started this program, I was like, why the heck am I studying a landslide? It made no sense for the first couple weeks until I learned more about them. So in the U.S. alone, they actually cause around $2 to $4 billion per year, and 25 to 50 deaths per year. And worldwide, that increases, as you can see the stats here. And obviously, some landslides are much worse than others. So you can get landslides that kill 100,000 people. There was one that took place in China around the early 1900s. And the Hawaiian earthquake here caused over 600 landslides and 200,000 plus deaths. So we want to figure out if there's ways to possibly monitor these things and have like early warning signs. An example of this can be seen in mining sites, as you can see here in Brigham Canyon, USA. There's a company in Golden, Colorado called IBIS who's actually doing some research on this right now. So before I get into the methods, I'll talk about some of the equipment that we used. The first one that we used was the Gamma GPI, which is a ground-based radar system. And this is part of the fieldwork we actually did, was taking this beautiful radar out there. One thing I want to point out is that the frequency of the wavelengths, which is like kind of how we use to measure this land information, is different. For Gamma, it's KU band, and it has a precision down to like roughly 2 millimeters or less. And same for the Sentinel, is a air-based satellite, and its band is C band, which is a different wavelength. And also, it's approximately down to the 1 centimeter approximation. So the methods. So what we did with the Gamma is we actually went out to Lake City, Colorado, to the landslide, and we set up 2 different locations with the radar. And basically, the point of doing that is to have produce a 3D images, because that's how your eyeballs work. So we set up these 2 different locations. We ran about 60 scans over the course of 3 days. Each scan lasted approximately a minute. And then we placed bolts in these precise locations to continue future recording of the data. And then once we actually got the data, we came back to the lab and worked on processing the data with the Gamma software. And let me tell you, Gamma software is a nightmare. There was only one person in the building that seems to be proficient at it, and he was hard to get a hold of, so processing the data was a challenge. But he got some pretty good results. And then the other method that we used to compare that was a Sentinel-1A, which is the European Space Agency satellite. For this, we actually were able to just go through the Alaska Satellite Vertex Archive, which is basically a website that has tons of data, and then we're able to select different images based on like the date, the path, the frame, and the time frame that you're looking for. So in selecting these data points, you want to find pairs that have good overlap. You can kind of see an example over there. None of those pairs, like each different color represents a different frame. None of those pairs are actually a good pair because they don't have much overlap. And you can kind of see like where some boolean is. And even like the turquoise green one and the red one, you might think that's good overlap, but it's actually not. So once we were able to find these pairs, then we can actually move forward in processing the data we get through the JPL INSAR ICE software. From this, we can actually create our digital surface models, which is kind of similar to the previous presentation. And from there, we're able to produce our interferograms. So what did we find? Well, we found out that the landslide is actually moving, which confirms previous studies. This one here is the Gamma setup. This is over a 24-hour period. And the highest displacement can actually be seen where you see like color pixel change, which is kind of up here at the top. And then this might be confusing. These little parts right here, those are actually, we think, is interference with the DEM images themselves. And out out here we actually have a lot of vegetation, so the vegetation produces a lot of noise. And the same thing can kind of be seen from the sentinel image. And most of the landslide movement seems to match up. You can kind of see it like in the middle of the landslide. All right, so over the 12-day images, we can see approximately, 0.2 to 0.4 centimeters per day, and then and so one of the issues we found with like the gamma data was actually in the spots that I was kind of talking about. We think that the magnitude is too big for that time period, and we think that's just because we don't have enough data. And that was kind of the problem with the research, is that we didn't have enough time to process everything. So 3 words of advice: never give up. We had a lot of time constraints to deal with, and the processing was a nightmare. As far as like learning how to process it, use Python, run the scripts. Future work would involve actually going back out to the site, which I think the group's going to continue on, and then we're also going to try to process the rest of the gamma data to get some better results, to kind of get rid of some of the pixelation errors that you can see in there. And I'd like to thank everybody you see here, RECCS, professors, and everybody you see.
All right, thanks. And I want to thank Joe for rolling with it today too. That stupid updated thing came up. I was trying to fix it first, so I appreciate you rolling with it.
Yeah.
I apologize for that. We'll fix that for the next round. So, any questions for Joe besides never giving up? Go ahead.
So you mentioned the possible connection to the other presentation using the drone technology. Do you think that would be effective in your area?
So actually, we did run drones out there, but like that's not part of the project I got to work on. I think it would be great. It seems to be great. It's kind of you still have to go do field work, but it's a great way to look at it and compare different data sets.
Seems like this is a larger area. Is this a larger total area?
Oh, I forgot to mention that. Yeah, the landslide is the active part of the landslide is about 3.9 kilometers long, and the total landslide is about 7, and it's about, I think, 300 to 400 meters wide. And like the speeds of the landslide actually vary depending on like where you go. They tend to like speed up in like the narrow parts in the middle. Let's see here. So like you tend to see like more movement like in these regions. You can kind of see the same thing over there.
So the size of the area and complexity, you'd have to put out so many marker points. It would just be a pretty big effort.
For the drones, yeah. Well, and that's actually part of the field we did was setting up ground control points for the drones, but that was like nothing I got to really touch on. I just got to experience it, have fun out there. So.
I have a question actually for you. So earlier on, because I know how much work you put into that. So the pairs earlier you talked about. Can you talk more about that and all the data that you went through to find the pairs?
Yeah. So for the pairs, I mean, you go to the Alaska Satellite Vertex website, and then you can kind of search your pairs, and then it kind of just pulls up. I think I went through probably 500 or 600 plus, if not more, like trying to find pairs that had good overlay, and you wanted to find a smaller time frame, because it seemed like if it was a long time frame, it was almost like too much displacement.
So between those.
So like day 1 to like day 28 versus like day 2, day 12, etc.
Lots of going through use too. How many did you use out of the 500 or so?
So I mean, I would search through probably like 600 plus, and then we ended up using 3 data sets, and then we ended up posting only one here, which you can see on the left. And so that's the 12-day repeat cycle, and this is the 24-hour repeat cycle.
Thank you. Any other questions? Or we can... Okay, go ahead.
So you probably said this and I missed it, but what's the typical speed for the slide?
It's about 1 to 2 centimeters per day. I think, I could be wrong, I'm pretty sure it's like 7 to 9 meters per year roughly. But it also just kind of varies like where you are in the landslide. Some parts can be faster, some parts can be slower. And you can kind of see here that some pieces that's not even moving at all, at least in like the time frame that we captured.
Okay, we'll do one more and then we should move on. So I'm gonna grab you and then we'll move on. Is that okay?
So you said part of your intention was to find some predictability in these?
I mean, just to kind of understand the landslide kinematics a little better, and then not necessarily like this group. I don't think they're trying to like figure out ways to pre-monitor it. Maybe they are, I know like IBIS, a company in Golden, Colorado, that's one thing that they like to do is they're actually selling their equipment to mining companies, and they're setting up the radar at these facilities or these sites so they can monitor for landslides to try to prevent them. Because if a landslide takes place in a, let's see here, there it is on the left. I mean that's a lot of damage done for that site right there. So yeah.
Well, let's thank Joe for her presentation. So that was our first half, if you will, of the program for that. So thanks again to all the speakers who've gone so far. And thanks for rolling with the camera and then making sure you project, which is great. So we're about till 2:10 for a break, so we start the second half of the program. If you haven't gotten one, there is a program that's printed out here at the table here if you want, and then the restrooms are going to be, if you come out this door and go this direction, you'll see a sign to the right for some past the atrium for the restrooms if you need it. So yeah, so I will see you back here in about 9 minutes. That sounds great. Thank you.
I had like 3 little things.
See you later. Thank you.
Joe, great job. That was so cool. Sometimes things sort of look different in the moment. The question. Well, there's sort of trade-offs about that. But no, that was great. I'm so impressed with everybody.
I was somewhere a wizard.
Despite technical difficulties, I think we're okay.
You just Cora?
Well, I think they could hear her just not well. You can go back to Maggie. No one said anything negative about the sound, except that was blessing. So
Okay.
perfect.
It's hard to go first sometimes on that.
Yes. Should I put one in a shared drive? Yes. And then should you
Yes.
Yeah. Oh.
No, just do the Google Drive. I can log in and don't remember the but before we do that, I'll get your drops and it's all good. You're a rocket. I should plug this in actually. Okay, charger. Let's do this real quick. We do have an end of the program. It's really fun. I have 2 chargers actually.
It's fun.
I'm just messing with you.
It's fine. I know I'm not going to start for another 2 minutes anyway.
Move the dog. Just move it.
I'll just do it from here.
If it makes you more relaxed, I'll go for it. Thank you. Yeah.
Those students teaches so that no, the natural
I know. So everybody, as you may have noticed, our cohort of students is running this presentation session with military precision. I've never seen a group of scientists stay on time like this, so thank you, everybody. If you just came in, we're doing 7-minute talks and 2 or 3-ish minutes for questions. And just to remind everyone, we're so impressed with extremely positive and forward-looking and constructive questions and comments for our speakers. So our first speaker in this session is Mike Moore, and Mike worked with Aditya Chupkulkar and Sunil Baidar at NOAA and with Ceres. So go ahead, Mike. Thanks.
So this summer, my mentors and I, we were trying to create aerosol profiles from Doppler wind lidar measurements. And just to give you guys a little bit of background on why we care about aerosols, they're tiny little particles in the atmosphere that can be like smoke or haze or volcanic eruptions or anything like that. but they primarily reside in the atmospheric boundary layer, which is the lowest portion of the atmosphere that's in contact with the surface of the Earth, which means that they can not only impact our climate, but also our health. But it's important to know that aerosols are not homogeneous throughout the boundary layer, and that the aerosols are actually really greatly influenced by the dynamics within that boundary layer. So the LiDAR is one way that we use to measure these dynamics, but it's not designed to measure aerosols or their properties, and instead they're actually designed to create or measure wind speed and direction and create like vertical velocity variance profiles. So this bottom graph is literally just showing the scanning patterns that the LiDAR at the NOAA Table Mountain Test Facility in Boulder is conducting. And this pie chart is just showing the amount of time that each one of those scans is conducting. But for this experiment, we were just using vertical stare data. So if we imagine our LiDAR shooting, like a flashlight shooting its laser out into the atmosphere, it's going to hit an aerosol, and then part of that laser is going to be absorbed, and part of it is going to be scattered. And so if we, that loses some of the light, and so if we measure the entire loss of light over an entire column, those are aerosol optical depth. But the LiDAR really just measures the backscatter, the portion of the laser that is refracted back directly to the LiDAR. But if we separate the total into sections, in this case 100 meters, we can actually measure that loss of light due to aerosols as a rate of unit per distance. So our objective, our goal was to extract that aerosol information from the signal data and create aerosol extinction profiles from there. And these are the steps that we took, which I'll walk you through. But first, if we think back to our flashlight, as you go further out in distance, the intensity of the flashlight decreases. And so it is with our LiDAR. And this is just modeling how the data that we collected is losing intensity as it goes further out. So this is our initial data, the signal to noise ratio. And this is just showing that, that as the signal is coming back, how intense that signal is. And this is still range dependent, and so as we'd expect, it's more intense closer to the instrument than it is further away. So first we need to correct that, and we actually use our range function that we calculated for before to normalize that. And so then we get the range corrected intensity, which is essentially proportional to our backscatter. Okay. And so this just essentially just shows the same thing, except without the influence of range on our data. But to get from backscatter to extinction, we need to, we normally use the LiDAR ratio, which is a ratio of extinction to backscatter. But from our measurements, we have a quantity that is proportional or representative of the backscatter, and so we need to really kind of create a modified version of the LiDAR ratio. So in order to do that, we have to pull from an outside source, the Aerosol Robotics Network, or AeroNet, and they provide us with that total extinction rate, or integrated extinction. And so now we have like all the information we need in order to create our modified LiDAR ratio. But our AOD is integrated, and so then we must integrate our RCI as well. And finally, we get our extinction profile. And so here we can see that in these little yellow structures, that the extinction is higher due to aerosols than other places. And it's important to note, though, that it's not necessarily an indication of concentration, because other properties such as size, shape, or type of aerosol also impact extinction. So just to recap, we went from our initial signal to noise ratio and down into our extinction, and we can clearly see there's a lot more going on, a little bit more structure to our aerosols. But tying it back to aerosol dynamic, or I'm sorry, the boundary layer dynamics, we're going to look at the vertical velocity variance, which is one of the products developed by the LiDAR. And there we can see that there's a lot of vertical mixing of the air. And shortly after, we have a higher extinction of aerosols. And then we also noticed that right around the same time and elevation, that our wind speed picks up. So these may be related, or they may not be, but that's kind of a study for another time. So we were successful in creating our extinction profiles, but further work still needs to be done to validate and refine these methods. But we're ultimately hoping that they will allow us to better understand and have a clearer picture of what's going on in the document.
Questions from Mike?
Right, of course. So you showed results from a single day.
Correct.
Your talk. Do you have results from other days as well?
Not here with me, but yes, we do.
Okay.
Yeah. So it's essentially a continuous scan. We did have some issues, in which case we had to turn it off for a week or two, but otherwise, yeah.
So you picked sort of a representative day?
Yep, just kind of like a kind of a day that I thought I could explain and kind of be interested in a little bit. Kind of show what's going on.
And so it looked broadly, looked like you had aerosols at a lower level initially, and then there was some kind of wind event, and then there were aerosols at a higher level. Am I interpreting that right?
Yeah. So part of the boundary layer dynamics is the radiative heat that the sun causes, and kind of obviously makes hot air rises, kind of thing. And so that's kind of partially what's going on with these as well, but also with the vertical velocity of the atmosphere as well.
So you make assumptions about the aerosol, like is it assumed that the aerosols all look the same?
Yes, so we are assuming the homogeneity of aerosols.
Okay.
Yeah.
And with are you assuming that they're all white and scattered light, or is there some absorption there too? I mean, is there some black carbon in there too?
Yeah, so we were assuming that they both absorb and scatter light. So we didn't specify which type of aerosol that we're assuming this homogeneous.
Yeah. I had a quick question. You may have said this at the beginning, but is aerosol extinction diagnosis what these Doppler wind systems are designed to do?
No, so this, this is really just, the instrument was initially designed to measure things like the wind profiles, speed and direction, as well as the vertical velocity, boundary layer heights, and those types of things. And just because it uses aerosols to make those measurements, we were trying to extract that information. So we're expanding the utility of this.
Did you catch any of the fires this summer? Oh.
Yes. So not necessarily directly, but it was on. Yes.
I mean, they showed up. Yeah. You can tell like today it's being
Yeah.
different than yesterday or last week.
Yeah.
Yeah, this has been an interesting summer to study aerosols for
Yeah,
sure.
for sure.
Lots of variation. Well, thanks again, Mike. We'll go to our next speaker. So our next speaker is Prudence, or Prue Cromer, and she's been working with Rick Saltis and Nisha Schnepp, Manoj Nair, and a whole team at NOAA and Ceres. Thanks, Prue. Go ahead.
Thank you. So my project over the summer was using the CrowdMag app to catalog magnetic anomalies from urban infrastructures and geological features. Woo! I want to tell you what geomagnetism is for those of you that do not know. So geomagnetism is the study of the Earth's magnetic field. Anytime that you use a compass, you use this Earth's magnetic field. When the needle points to north, that's magnetic north. So, the Earth's magnetic field, navigation. What CrowdMag is, it's a smartphone app that has been developed by the geomagnetism team. This is the first developed crowdsourcing app. Any of you can download it and start recording your local magnetic data. So I encourage you to download CrowdMag. The app accesses, or the phone accesses, the built-in magnetometer. And what a magnetometer is, it reads the magnetic data. On the app, it displays nanoteslas, which are the measurement of the magnetic field. So satellites pick up on a broad global span of the magnetic field, and they look at several kilometers of this magnetic data. But with CrowdMag, we can actually hone in and look down. We can look at this magnetic data within meters. So you can look at the details of the local magnetic data. So what is a magnetic anomaly? A magnetic anomaly is a deviation in the Earth's magnetic field or an interference in the Earth's magnetic field. So this could be a bridge, an iron pipe, rebar, any overlying or underlaying metal that throws off the magnetic field. So the purpose of my project was to catalog these local magnetic noise sources to improve accuracy in the magnetic navigation systems. And with the collection of these noise sources, we can create maps, graphs, and different mathematical models for the magnetic field research. The two questions that I investigated were, what are the general characteristics of the urban infrastructures observed and modeled using CrowdMag and Excel? And the second question I looked at was, would these characteristics be useful for magnetic navigation? So here I just want to show you what a magnetic anomaly looks like versus a non-anomaly. So here we're looking at a plot of an area behind the CU campus. We had 9 CrowdMag users and 1 external sensor user, which is, it's another magnetometer, it's more precise. So we all went out, we all collected this perimeter of this course, and we looked to see if we can identify any magnetic anomalies. So here we can see there's an increase in amplitude, there's an increase in the magnetic field. So this would be considered an anomaly. And then here we have a secondary interference that we can identify. The flatter lines are considered the non-anomalies. There's no noise going on from what we can tell. I did spread this data out so you can see the comparison of each individual user. So I created a catalog. I wanted to first show you the geological feature that I collected, or we collected. We went out to near Ferncliff, Colorado, and we were looking at an iron dike. A dike is a geological formation. So we originally thought the iron dike was over to the left. We thought it was originally in one area, and then when we went out and collected with our CrowdMag app, we looked at the magnetic data, and we ended up finding the iron dike actually further west. So there was an increase in the amplitude. So here again we were observing this area, and boom, there's the iron dike right there. So with CrowdMag, I thought that was fun and interesting that we identified where the actual location was from the iron dike. And then I cataloged different urban infrastructures. So here we have 2 different pipes. This looks like a lot of data, but I'm going to break it down. So this first top plot here, it's showing the observed data of the magnetic intensity of this iron pipe. The second plot here, this is an illustration of forward modeling. So I tried to create a spherical model matching the best fit for the observed data, like above. And what this shows is the shape of the magnetic anomaly. Down below, this plot here, this shows the depth. So we have meters for the depth and then the distance in meters. So you can see this iron pipe, I actually walked under it when I recorded it. So it was 3 meters above the ground. And this is what these bubble plot looking features are. These are the magnetic features that I picked up on with the app. The red indicates on higher intensity, and then the yellow is the less intensity. But these are illustrations of forward modeling. So these are the 2 pipes that I looked at and was analyzing the characteristics. Then I looked at bridges. So we have a smaller bridge to the left and a larger bridge to the right. So we looked at the different amplitudes, the peaks that you see here. I demonstrated a linear trend, just the increase in the magnetic field, and again, the depths of these magnetic anomalies. And then this bridge, obviously there's more metal, so we're displaying a number of different peaks that we identified. Yes, more magnetic data to pick up on for the interference. So just to wrap back around, we successfully identified these magnetic anomalies as magnetic effects using CrowdMag. With those models I just showed you, we could identify the depths and the strengths of the magnetism, the magnetic intensities. And with future data collection, we can aid in alternative navigation. So we can possibly use these urban infrastructures for mile markers for alternative navigation. I would like to thank Rick and Manoj and Nisha and Brian for being patient with me and believing in me, and of course the RECCS team, yes, and the National Science Foundation. Thank you.
Okay, great. A couple questions for Prue. We may have to exclude Rick. Okay, Joe.
It's kind of an easy question, possibly. If you're the earthquake or the equator, you have the device that would point north or south.
That's a
you
good
said
question.
Rick, you can help
Get
me
an
answer
answer.
So compasses still work at the equator, and you like to think that compass, but the magnetic field is very different at the equator than it is at the pole. So the main direction of magnetic field at the equator is horizontal, and at the pole, the strongest direction of the magnetic field is vertical. So depending on the type of compass you have, if you have just a physical compass, it's not going to be working as well necessarily at the equator.
It's not
going to have as strong of a signal necessarily.
I was wondering if it would be like at least sideways based off her kind of first description.
Yeah, but actually, if you get too close to the pole, your needle wants to actually go down.
We may have to all go to the equator.
Well, the other cool thing is the magnetic equator is not the same as yours.
One more kind
Just
of
like the magnetic poles.
time for one more question for Prue before we switch. Anyone curious about using
I'm just curious about the app. Like, how many people are on it, and is it well used? And
I don't know how many CrowdMag users there are, but you should download it if you haven't. I know.
There's around 30,000.
Okay.
Well, thanks. This is something that we don't even know, but it's influencing us as we try to get around town. Thanks. All right, let's change. So we actually have another speaker addressing issues of magnetism, geomagnetism. And there may be a quiz at the end on some of the this is Kelly Sullivan. She has worked with Sam Califf at NOAA, and she'll take us more into the world of magnetometers.
all right. So, for my project this summer, I was using GOES magnetometer data to quantify the error in magnetic field models near geostationary orbit. So I'm sure you guys are probably wondering what on earth I'm referring to. So I'm going to give you a big overview of exactly what all of this means. So we have the sun, which is just basically a big swirling massive plasma, and which is basically superheated particles.
which is constantly emitting a stream of charged particles towards the Earth. The Earth shields us from these charged particles by its magnetic field, or magnetosphere. The shape of the magnetosphere is constantly fluctuating just because of this interaction between the sun's forces and the magnetic field, which is called geomagnetic activity. So these fluctuations are modeled and predicted with something called the TS04 magnetic field model, but the measurements themselves are taken by satellites that are orbiting the Earth. So the satellites measure the magnetic field in nanoteslas, and as far as the reason that we care about any of this stuff, there's so many sectors that we so heavily rely on that this information is essential to. So anything from telecommunications, power grids, radio communications, aviation, all the way to human space flight. So for my project, we looked at GOES-16. It's a geostationary operational environmental satellite. There's 3 others currently in operation, the GOES-13, 14, and 15. As you can see, the orbit's represented here. The geostationary orbit is basically around the equator, and all the satellites are fixed to a certain point on Earth, rotating at the same speed as the Earth, so it makes a full orbit every 24 hours. Each of the satellites has 2 magnetometers, an inboard and an outboard. They all measure the magnetic field in 3 directions. The earthward direction that points towards Earth, the polar direction which goes directly up from the satellite, and normal, which basically just traces the path of the satellite's orbit. Currently, GOES-16 has an issue between its onboard and its outboard and inboard magnetometers. There's disagreements in the measurements that they're getting. So, how do we go about diagnosing those issues? Our idea was to evaluate how accurate the model is at geostationary orbit in order to figure out these issues. So, we decided to focus on 2 components. Does the accuracy change as a function of magnetic local time, which is basically just where the satellite is on its orbit, as represented here? And does the accuracy change as a function of geomagnetic activity, which is just those storms that I was talking about earlier? And it's represented by the KP index. So if you think of it sort of like how they measure hurricanes on a scale from 0 to 5, if you are at the top, then you're talking about a really strong hurricane. So I know this looks like a lot, so I'm going to break it down for you guys. So what we have here is a quiet geomagnetic activity day and a stormy day. As you can see, on the stormy day, there's a lot more peaks, and I highlighted in yellow just sort of how, to show you how variable the actual activity is as far as the measurements in nanoteslas. On the x-axis, we have the time of day. On the y-axis, we have the measurements in nanoteslas. So the first panel, this top panel, we're looking at the solid lines are all the measurements from the satellites, and the dashed lines are the model's predictions. The next panel, we have the error or the difference between those 2. And then in this bottom panel highlighted in red, we have the difference between the onboard and the inboard magnetometers on the GOES-16 satellite. So you can see that regardless of the geomagnetic activity levels, there's still differences in the measurements. It should be just straight at 0, but right now it's not. So what we did is we collected data for all of the GOES satellites, and we made plots like this one here. This is GOES-15, of the error between the satellites and the model for all of 2017. So the height of these columns represents the number of times that the error occurred. Where the actual graph is centered represents the mean or the average error. The standard deviation, or basically how wide the graph is, just represents the variability of the error. So we fit a curve to all of these histograms to compare statistics for different cases listed here in this table. So what we found is that according to magnetic local time, or where it is on its orbit, in these charts of GOES-13 and 16, we were looking for a, we were comparing data taken at different times in the satellite's orbit, so dawn, noon, dusk, and midnight. So what we were looking for is a shift from the peak of each distribution from 0 as a function of MLT, which would indicate a systematic error, a systematic bias in the model. So for GOES 13, 14, and 15, which is just represented by this one here on the left, you can see that the error is about 3 nanoteslas, or this bias shift, whereas for GOES 16, it's significantly more with about 8 nanoteslas, which indicates that the P component of the magnetometer of GOES 16 has some sort of issue. As a function of geomagnetic activity, or how strong these storms are, we split up the data by KP, and we find that the model performs better at low KP, just because, as you can see with the low KP, which is the blue line, it's more peaked, which means there's less variability in the error. And we actually calculated how much of a difference there was, and there's significantly higher accuracy at low KP. So as far as the big takeaways, we found that model accuracy depends on the direction of measurement of the magnetic field, and that there's a systematic daily bias with MLT, which varies significantly more for GOES 16. And the model is more accurate at quiet KP levels. So with that, we have quantified some of the accuracy of the TS04 model, which will be useful in understanding issues with not only GOES 16 and its magnetometers, but also future instruments that we'll use. So, references, right on time. Okay. And acknowledgements. Thank you, Sam, for bearing with me. And for all the RECCS students, because I know sometimes I lost my cool a little bit, but you all just calm me down, and you're amazing. So thank you, and for all the RECCS team.
Any questions for Kelly? This was a lot to absorb, so just let it sink in.
I'm hoping that the Geomag team will not ask any questions.
You are now allowed to ask questions.
Oh, wait, here we go. Okay.
So why don't you go back to your graph with the blue and the green?
Yes.
So does the blue and the green, are they both on the same scale on this plot?
As far as
so the height, the variable height between the two, that's a true variation between those.
Right. Just as far as how often
You're using the same axes for both curves. Is that
yes, I believe so. Yes.
And then you said that you felt like the blue ones were kind of less spread.
Right. So it's a little more. It's more peaked, which basically means that there's less randomness or variability in the errors that we were seeing between the model and the measurement. So because of that, the high KP are just sort of hills, sort of slopes, whereas those ones are more peaked, which just basically shows the error isn't quite as distributed. Anybody else? I guess that's a good thing about having a complicated topic.
Can you tell us some of the implications of what you found for maybe, will there be steps made now on the satellite to correct anything, or is there, things are not quite maybe to that point?
Well, this just kind of gives us a step in the right direction. As far as GOES 16, honestly, I was talking with Sam about how you can just go down a rabbit hole of all these comparisons that you can make in order to evaluate exactly how accurate it is. But from where we're at right now, we can just use the model at the times where it seems most accurate to really figure out this comparison between the outboard and the inboard magnetometer and why those are having issues, if it's with different components or kind of where those are occurring. And then also, like I said, you can also use this information for future instruments that are going to be future magnetometers and different satellites.
Yeah, great. Yeah, any other questions? Or we can also follow up with any of the speakers at the end, the reception time, if you have any digesting time for lots of information. So thank you so much, Kelly. That was great. right, our next speaker is going to be James. Good. So James Button from Northeastern Junior College worked with John Albers and Juliana Diaz. And he also has a lot of great information for us to process, so take it away.
Hi, so my project was the subseasonal to seasonal forecasting, which is the gap in our ability to predict hazardous weather. So last year, February 2017, in Oroville, California, there was a Oroville Dam crisis where they had a surprising 15 inches of precipitation that they were completely unexpected. And due to this, the dam came very close to failing. It actually was successful in not failing, but it threatened it so much that they had to evacuate 188,000 people. So, well, that was why it's important. So our meteorologists are able to make forecasts up to 2 weeks. Our first week is really good. Our second week could use some work. And then our third week, it just kind of falls apart at. And so we're also really good at making predictions, like climate predictions, past 3 months. So we can tell you like what fall is going to be like, what winter is going to be like, and all that. So what we're actually trying to predict here is this polar jet stream in this picture here, where most of our weather comes from. And the atmospheric conditions in that area are so very chaotic that is the reason why we can't get past 2 weeks. So what meteorologists do is that they look for windows of forecast opportunity, which are times when our forecasting skill is increased. And one of the ones that we decided to take a look at was El Nino, which I will describe in detail soon. So essentially what we did was we used coding to pool forecasting data from our European models and pool our observation data, what actually happened during those days, from our Japanese reanalysis data models. And these were for the years 1996 to 2014. This data, after we got it, we were able to remove the climatology for the past 35 years or so, which is what tells you what an average day is going to look like, what, I don't know, February 2nd is going to look like 35 years in a row. And so what this information does is when it pulls from those models, it gives us anomalies, what a day is like going to be too hot, too cold compared to the average. And then these anomalies are sent to an anomaly script file, which gives us a correlation between the two. And this correlation can be plotted onto maps, like so. The variable that we are using in plotting these is mean sea level pressure, too. So then we split it between our week 1 and 2 forecasts, our week 3 and 4 forecasts, and our week 5 and 6. As you can see, this is our current forecasting capabilities. So our week 1 and 2, pretty decent, not too bad. A red and orange map tells us that we made, more often than not, we made good predictions. And we were doing it based off of really good information passed back from models. Our week 3 and 4, it starts to get to the yellow, and that's actually not very good because yellow means that we're at 0.3, 0.4, meaning we're a little less than half the time right. Our week 5 and 6, most of the map is white, which means that we were just taking blind shots in the dark. So to counteract this, we decided to take a look at the El Nino Southern Oscillation to see if it would provide that window of forecast opportunity. And it actually does, but what it does is the Pacific Ocean sea temperatures start to warm up, and this causes convections in the atmosphere. These convections shift that polar jet stream down and causes warmer conditions in our northern states, drier conditions in our eastern states, and rainier and wetter weather in our southern states, like so. And so it actually does cause quite a bit of flooding in the southern states. This was actually taken from California, Southern California. I'm not quite sure the year, I think it was 2 years ago. So what we did was we went through our models and we redid the years and changed it to 2010 and 1998, which were 2 years that we had El Nino happen, and they were particularly strong years. So with our week 1 and 2 forecasts, we had a lot more dark red in our maps, which means we already started off much better. Our weeks 3 and 4, we had a little bit darker yellow, which means we're still doing good at that point. And then week 5 and 6, we actually had more yellow over the map, so it did increase our forecasting capabilities. The blue correlation here actually tells us that our models was passing back data that was just completely wrong. So the nice thing about that, at least, is that we can at least have some information so we can look at where we were going wrong. And so taking a look and comparing weeks 3 and 4 for both the El Nino years and the full data set, we can tell that definitely when El Nino is happening, we do have that forecast of opportunity and our forecasting skill is better. So using this information, one of the issues with El Nino is that it only happens every 3 to 7 years. So because of this, we might want to start looking at other oscillations and other windows of forecast opportunity, because this 3 to 7 years is a little unreliable. And not only that, but El Nino has variations in its strengths. So we could also look at other variables. I mentioned mean sea level pressure earlier. We can also look at how the temperature looks and also how precipitation is. And then we could also use other models other than our European models and our Japanese models as well. So I would like to say thank you to my mentors, John Albers and Juliana Diaz, as well as the RECCS team.
Thanks so much. Any questions?
So I had a chance to talk to you at the poster yesterday, so I've already answered some of my questions. But so your finding is that during the El Nino period, there's the 3-week forecasts are more reliable.
Right.
So do you think that's because the weather is just more steady, or that the models are better during that period?
It is actually because we have, when that, let me go back to the slide real quick. On this picture, when the jet stream gets moved down like this, it actually has a little less breathing room and has less chaotic conditions to account for. So it's increasing our ability to be able to account for all the factors that are in the atmosphere at that point.
Because basically less variation happens. So if
Right.
you say the weather tomorrow will be the same as today, you have a way greater chance of being correct.
Right.
In the last 3 years showing like that for the ENSO, it was like much better at predicting like 3 to 4 weeks ahead, but then you had areas where it was like completely wrong. But were those areas like consistently completely wrong, or did it kind of like move around?
Yeah, they were, it was tending to be the areas where we have forecasts that was, or models that were giving us information that was just wrong. And actually, one of the reasons why we have blue on these maps is just due to the fact that on El Nino years, we were only counting 2 years versus 20-year averages. So if we looked at individual years from 1996 to 2014, we would have blue on those models as well. And that was just, it's not as often that that happens, so that's why it didn't get shown on the other models. But yes, it does, it passes back incorrect information that we can actually learn off of. And it just, we were making wrong predictions more than we were right, so.
I was curious about an event in Boulder. Did anyone go through the 2013 floods here and have their houses flooded? And do you know whether that event was predicted accurately, or?
I'm not real sure. I actually don't know exactly, other than those 2 years, what other years that El Nino happened, but it could be similar to what they had in California last year when their dam was about to fail. That was not an El Nino year, and they got a massive amount of precipitation, more so than they'd had in any winter 100 years past. So it could have been a completely random event, or it could have been an El Nino. So
my actual weather app can predict weather up to like 1 month later. But your analysis says that you cannot predict anything about 3 weeks. So is actual weather live?
that is a great question.
You can predict it, you just can't predict it accurately.
Yeah.
Yeah, I was worried about that question.
Yeah.
You can trust CrowdMag, but be a little more wary of AccuWeather. Talk to James first.
So do you think there is a reason then that you found better correlation in weeks 3 and 4 around the center of the continent?
Well, actually, a lot of those could just be due to like what is the word? Just the way that the land is. Like one thing that I noticed when we were going through our first data set is I plotted it over the whole world. And back when I didn't really know quite what I was looking at, my mentor John was actually there and he was like, oh yeah, this area is this because that's the Appalachian Mountains and we have less predictability in that area. And he knew the map that was already on there and I had no idea at that point. So it could very well be just due to geographical areas. So.
Well, thanks so much. We'll move on to our next speaker and follow up with Jen. I'll introduce Susanna as she's coming up because she may be something like 29 seconds behind.
Great job timing.
Yeah, this is great. So Susanna Rozak worked with Ariel Morrison and Jen Kay and Anna Gold and others at Series. And she's going to talk to us about a very engaging subject.
Start off with a pun, I like it. So, most of us here are students, or at least are former students, teaching, working at schools, or whatever. So we've all done a lot of different types of educational activities. And some of those have worked really well, and some of those, as I'm sure you can think back to, are not quite so successful. We know that the most successful activities to help learning games are the ones that you're the most engaged in. But generally, when we've looked at how engaging a certain activity is, it's been a lot of just subjective data. You know, Kogi, how engaged are you right now? You know, that's just, who knows? We're scientists. We like to have objective numbers. So we've tried to use hand sensors to determine engagement when talking about climate change. Determining student engagement in climate change education with the use of hand sensors. So how do we do this? We know that the higher engagement leads to higher learning. We know that the more engaged you are in something, the more you actually sweat. And there's been a whole bunch of studies that have shown that. And we're talking about your ecrine sweat glands, not your apocrine sweat glands. These are just really lightweight. You don't even notice that they're covering your body. Believe it or not, the more interested you are in this presentation or previous presentations, you're actually sweating different amounts. And the more you sweat, because sweat is very conductive, the more electrodermal activity, or EDA, you'll have. Basically, the higher your skin conductance is. So we use these hand sensors that are similar to Fitbits that actually measure your EDA. So for our study, we had 52 students just recruited from CU Boulder here that we divided into groups of 3 or 4 and had them do a variety of climate change activities. These students, luckily, were pretty representative of CU Boulder's population. It's always a little concerning when you're recruiting people that you're going to get, like, I don't know, some random bias somewhere, but we got pretty lucky here. So one of the problems with these hand sensors is that everybody's skin conductance is different. Some people are really sweaty, some people are not so much. So it makes it really hard to compare against large groups of people. So we had every student collect a baseline before we even started any of the educational activities. We had them sit quietly with their hand sensors on and recording for 3 minutes. And then when we would compare these against the activity, we would use their percent difference from the baseline. And you can see these sensors are very sensitive. These little peaks here, that's just from the act of pressing the button. Every time they pressed the button on their hand sensors, it made a little red mark there, so we would know what was going on. And then we moved on to their activities. They took a little short pre-test just about climate change. They watched a video. They did a worksheet about the science in the video. Then they watched the same video again, which I will discuss in just a moment. Then they had a group discussion about the imagery found in the videos. The last activity was an open-ended climate change question, and then they completed a short post-test. So for the videos, we had 2 different videos. One of them unique polar processes. The other one was our shared climate future. Each video had the exact same science, but just different versions. One had polar bears in it, one it did not. And the reason why we did this is because polar bears have long been used as like the poster child for climate change. And so we wanted to know, well, are they actually effective at getting people engaged in climate change, or maybe should we move on to something else? So this is what our results look like. This is just the raw data from one student. Throughout the study, we have them press the buttons on their sensors, like I mentioned before, to give those little red marks. And some of the activities we have them press multiple times, like this entire section here is the worksheet. They actually press the button 4 times during that activity. And you can see, you know, their EVA does, their conductance does change pretty dramatically throughout the study. One thing that we were really interested in was previous studies have shown that videos are super engaging. That's not what we saw. This is just a close-up of 2 minutes from one of our subjects, and you can see that the video was pretty low, pretty flat. They were pretty bored. And then we asked them to talk. All of a sudden, their engagement level skyrocketed. When we looked at whether they saw the bear version first or the non-bear version first to determine the effectiveness of polar bears as engaging, we noticed that while there wasn't a whole lot of difference if they saw the bear version first, which is the one in red here, it did increase when they saw the bear version second. We correlated this with what they said during the study about what they found most interesting. We discovered that they were basically noticing differences. They were playing Where's Waldo with polar bears during the second video, so that was why they had a higher engagement. We compared a bunch of different demographics too. We wanted to know, like, do men find certain things more engaging than women, or political groups, or whatever, and we didn't really find a whole lot of differences except for STEM versus non-STEM majors. Non-STEM majors, as here in blue, were much more engaged during the discussion and the open-ended audience question. And when we asked them about this, we noticed that the non-STEM majors used words like nervous or anxious when having to speak about a topic that they were less familiar with at a far greater rate than the STEM majors did. Which is really interesting just by itself, but especially because this was really good support for the idea that the data that we were getting from the hand sensors really was accurate, and it really is a good way to measure engagement. So basically, our baseline protocol that we did to compare against large groups of people was very effective. We were really excited about that. The highest engagement was during speaking activities, even though this does differ from previous studies, so I think we'll definitely want to go into that a little bit more to find out exactly why that is. Polar bears, we're still kind of on the fence about. It does appear that polar bears can be an effective emotional hook, but you know, the order of the videos mattered, so we don't really know about that. And the non-STEM students were definitely more engaged when speaking about climate change than STEM majors were. If you want to look some up, there's some other references for you. And thank you to everyone at Sears, RECCS, and everyone in Jen K's department.
There might be tons of questions about this, but let's just take one now before our reception time. Jason. Go ahead.
Oh, I don't know.
No, oh, I'm so sorry. Okay, let's see. Can we hear from you, please?
Sorry about that.
Can we buy this sensor?
You can. They're $1,700 each. So I'm really interested to buy. Is there a student discount? Probably.
Let's see what Jennifer's question is.
I'm really interested about your thoughts about maybe having, when you're doing a video, breaking it up with discussion between, just to see if that might change the engagement of the video.
Right. We thought about doing it that way. We wanted to do all the discussion activities afterwards, though, because we were worried that if they did get all engaged during those discussions, that then the second viewing of the video would be like artificially high because they were still so engaged in the previous activity.
Go ahead.
How do you separate engagement, say, anxiety? Like people
Anxiety is a type of engagement, honestly. So we didn't really separate between the different types of emotions that cause this engagement. We were just looking at engagement, period. Looking at whether certain emotions like anxiety would produce greater learning gains or something would be a very interesting study, but one that would take longer than the few weeks that we had.
And you know, I think we should defer questions till our reception time, which is in about 10 to 15 minutes. But thanks, Susanna, and come on up, Jason. So Jason is our very last speaker in this series, and he worked with Jen Kate, like Susanna did, in the SEEK building. And something to mention about Jason's situation is that he was partially funded by a career grant to Jennifer Kay, and he is actually currently a CU Boulder undergrad. Some of the rest of our group are future CU Boulder undergrads, but Jason is currently here, and we'll let him explain his climate modeling study. Thanks.
Hello. So this summer I studied cloud feedbacks within several different modeling experiments, and we specifically focused on cloud feedbacks in warming and cooling scenarios. And in order to study the climate, one thing that scientists do is they run experiments on general circulation models, which are just millions of lines of code that basically are run on a supercomputer, and they contain everything that we know about the climate. And one of the common experiments that scientists do is they perturb greenhouse gas levels, and then what you can do is you can study the net radiative flux through the top of the atmosphere, which is defined as the difference in the net shortwave radiation that's coming in from the sun and the outgoing long-wave radiation that's emitted by the Earth. And by studying the changes and the differences in this radiative flux, you can estimate differences to temperature changes and other variables that we're concerned about for the future and climate change. And also, just a climate feedback in general is something that affects the net radiative flux once you have some sort of radiative forcing that has occurred. And cloud feedbacks cause one of the largest sources of error among these models, and it's because, as you can see here, a cloud will not only reflect the shortwave radiation that comes in from the sun, but it also absorbs and re-emits the long-wave radiation from the Earth. So it's affecting both the shortwave and the long-wave radiation. So it has a large effect on the net radiative flux. And the cloud feedback model intercomparison project is basically just focused on improving the representation of cloud feedbacks in these models. And we performed a CF-MIP endorsed experiment that was run on the Community Earth System Model 1 Community Atmosphere Model 5. And we asked the question, are cloud feedbacks linear under both warming and cooling conditions? And so we started with 1850 initial conditions. We used data from all three runs. One of them, the third run over here, I actually ran on the Community Earth System model. We ran it for 45 years. In our control run, we held CO2 concentrations constant. In our second run, the CO2 concentrations were initially doubled and then held constant. And then in the third run, the CO2 concentrations were half and held constant. And going into the methods, in order to actually calculate the climate feedbacks, we use the radiative kernel approach, which is described in Soden et al. 2008, which is a fairly long technical paper that basically describes how you can break a climate feedback apart into two different terms. One of them is called a radiative kernel, which is just dependent on a climate response to changing a feedback variable. So if you change the temperature by a little bit and run the model for a while, you see how the radiative fluxes change based on that. And then the second term is dependent on the radiative transfer algorithm of like an unperturbed climate state. So we were comparing our control run to like the double and a half CO2 runs. And this simplified, and also just to note, the radiative kernels we used were pre-calculated by Angie Pendergrass, who's a scientist up at NCAR. And the overall process for the experiments that we ran on the model is just like kind of given in this graph here. We change the carbon dioxide levels. We cause a radiative forcing, so you're no longer in equilibrium. And you then go into a climate response where your temperature changes because the climate wants to go back to equilibrium. And the change in temperature then causes other feedback variables like cloud cover and water moisture to change in the atmosphere, and then that further affects the net radiative flux, which will then further affect the temperature change. So you get this loop. And we specifically focused on the cloud feedbacks. And eventually, these feedbacks are positive and negative, and they will bring the climate back to equilibrium, and you end up with a new temperature. And so the important question first to ask is, did the climate actually warm and cool when we doubled and halved CO2? The answer is yes. However, the warming and cooling wasn't linear. We found that in the cooling run, the temperature cooled by 1.54 degrees Kelvin, but in the warming run, it warmed by 1.89 degrees Kelvin. So there was a 0.35 degree Kelvin difference between the magnitudes of the temperature change. And that means that there was some sort of climate feedback that was causing this difference in magnitude. And these three climate feedbacks we found were linear. The temperature, surface albedo, and water vapor feedbacks all had about the same magnitude. So it means like between both the warming and the cooling run, they were affecting the net radiative flux about the same. So we looked at cloud feedbacks, and you can see the magnitudes for the shortwave, longwave, and total cloud feedback were all different in these runs. And it's also important to note that for the doubled CO2 run, we had a larger total cloud feedback than we did in the half CO2 run, which also corresponds to a larger change in the magnitude of the surface temperature. And this makes sense just because a more positive climate feedback is going to contribute to a larger temperature change. So here are just two graphs of the shortwave and the longwave cloud feedbacks that show the actual values along latitudes. You have your south pole to the left and your north pole to the right. You can see the overall shapes are fairly similar, but there's some pretty dramatic changes in the magnitudes of feedbacks, which makes sense since we didn't find the same magnitudes in the overall global average of the feedbacks. And here's the total cloud feedback again between like around 0 and 40 degrees latitude, or 40 degrees north. There was like the most dramatic change between the halved and the doubled CO2 runs. And going on to a few discussion points, I guess the main takeaways are we had a nonlinear temperature change between the two runs that we didn't exactly expect to happen, but because the cloud feedbacks were not linear, this explains this nonlinear temperature change as well, because as I said, like a more positive climate feedback is going to contribute to a more like a higher value of warming or cooling in whatever scenario that happened. It's also important to note that the total cloud feedback was positive, which is consistent with other studies that have been looking into cloud feedbacks. And the double CO2 feedback seemed to contribute more towards a temperature change than the half CO2 feedback. And so for future work, we only studied 45 years of model output data. We want to bump it up to 150 years just because the CFNet protocol has these standard projects that they want you to compare exactly against different models, and they ask for 150 years. We also, I wasn't able to show you in graphs, but the climate doesn't reach equilibrium after 45 years. So we want to study like the temperature change once it actually goes to equilibrium, or it's very close to it. We also want to incorporate a more robust method to account for cloud masking and greenhouse gas forcing, because we think we can improve on the estimation that we're making for that. And currently we just have a value that's saying these global averages of feedbacks aren't linear. We don't really know why, so it would be interesting to go into looking at the changes in the cloud cover over different latitudes and how they're interacting with other feedbacks to actually maybe look at why this is happening. So it's pretty much the conclusion for the project.
Well, any questions for Jason about clouds, models, linearities, or non?
I was just curious, with your models, use like initial conditions from the year 1850, and you're in it for 45 years. So like, what's the reasoning behind that?
So the reasoning behind the 45 years was just time. It takes a really long time to run the model. Currently, I have data up to 100 years. There's also a problem with storage space. It's like 9 terabytes right now, and don't have much more room to get to 150 years, so we'll have to figure that out. But it was mainly time for the 45 years of data, and then how you actually get to 1850 initial conditions is you set the model like back to those conditions, but then you have to run it out for like 300 or 400 years to let it reach equilibrium. And we wanted to get like a pre-industrial, I guess, like look at what would happen, just because that's around the time when we started emitting a lot of carbon dioxide into the atmosphere.
Yeah. So you had some cloud state for by latitude. Yeah. So that traditionally, in the climate studies, they often say that the greater effects of climate change are seen at the poles and less so at the equator. But this effect seems to be on
It's more the tropics and the equator. Yeah. Not entirely sure why that is. I think one of the reasons might be there's a lot more clouds at the tropics than there are at the poles. Just with the whole circulation of the Earth, you have a lot of at the poles. You have air that's like going down, it's sinking. So clouds usually form with rising air. So there's just not a lot of impact of clouds at the poles to begin with. You have a lot more rising air in the tropics because you have warmer temperatures. That's probably one of the reasons. There's also, this is just, I guess, a side note that's interesting to note. You can see right here, the have CO2 runs actually start to shift more towards the equator as well and away from the poles. I'm not entirely sure why that is, but that's something we have to look into.
Great, well, thanks so much. Let's clap for Jason and all the students. Yeah, make sure to hold your saved questions in your mind for our reception time. We wanted to thank our communications team.
Yeah, this summer, I forgot earlier. So the comms team at Sirius have been amazing help this summer. So Kitty Weeman's helping us do photography throughout the summer, and we had elevator speeches, videos that are actually also online for that. And then also kind of helping us, her whole team helped us get some outreach, I guess, with David Camera and Cable or Daily of articles on RECCS this summer. So thanks to the comms team for that.
So now, as I mentioned, I'm going to go through a few quick highlights of the summer and individual awards and recognition for each of the students. You probably gathered that their projects were really different. There was a huge sweep from climate change in polar bears, climate change in clouds, to apps on our phone, crowdsourcing data, to landslide adventures and beaver ponds, and let's see, what am I forgetting? Aerosols, extreme weather events. I learned a ton across all those different fields, and I put together some both kind of formal and informal recognitions along the way. So one thing I wanted to say is at the poster session yesterday, each of the students that just presented had a poster on a stand, and they stood in front of it, and professional judges and or judges and scientists and professionals in training came by and talked to each of them about their work. And all they had to kind of go with was this one fixed poster with some of their images and some of their graphs and charts that they just showed today. So that was a very different setting than now. And I think, let's see a show of hands, which found the poster session more fun and which found the presentation? Who votes for posters were more fun? Okay, interesting. How about presentations? Who found the presentations a little more fun? Okay. So we'll kind of get back to that because our judges, this was a learning experience summer, so we didn't have grades, but we were looking to acknowledge people on certain strengths, and in some rare cases, the judges would comment on areas to improve in the poster session. So I'm going to go through some of our findings here. First of all, back to the early summer. This is our group. In the wild, the RECCS staff over the years has come up with some team building adventures and made them stand on like tilting beams and do a group hug or something. I think I missed this part.
Yeah, they were. It was the last year, the Mountain Research Station with our friendly guide over here for about a day with her, 2 days with Deb, I think. one team building activities. That was the most interesting for me. That was really fun watching them figure out how to get around the laws without falling off.
And at this point, they really did.
And okay, we'll say something about Joe. So Deb's been doing this for years, and then all of a sudden Joe found a loophole, and she goes, "Well, that's a new one, and it actually works. All right, I'm done." So she was impressed with the teamwork for sure of that.
Right.
So.
And this was like day 1 or 2, so the team didn't really know each other at that point at all. So we just sort of turned them loose to get to know each other and kick off their research summer. And then they actually transformed into very professional, early career scientists on campus. This kind of a mid-summer look, or early to mid-summer, and now you've seen them today really giving talks in the most professional manner that I could imagine. So it's been quite a journey. And as I mentioned, the judges at the poster session yesterday each looked at 3 or 4 different presentations and posters, and they came up with several themes of recognition. So outstanding communication skills with all the visitors that came to their posters were Kelly, James, Davin, Sean, and Prue. So let's give them a hand. The visitors were from different disciplines in the fields. Some of them were from different countries. They weren't native English speakers. They had all kinds of questions for you guys, and they commented that these 5 students did overall the most outstanding job of kind of across that breadth of question and answer. There was also excellent question and discussion sessions in particular. This is another type of skill. And we have Jess, Mike, Susanna, and Joe recognized for this. These were side discussions or main discussions with the judges that were just noted as outstanding. So, and then the third type of award was for really exceptional content and layout and sort of flow of the poster. And we'll come back to a little bit of this, but Cora and Jason were recognized there. So nice job. So we actually have some more general awards that have some of these same themes. And for these, we'll ask you to come up and grab a certificate. We have both a high-tech professional certificate and a more low-tech additional certificate from the 2 of us. So the first one is to Cora for her creative poster design. Cora looked at Petri dishes all summer long, as you could have seen in her talk, and it began to influence her to the point where she designed an entire poster to look like a large Petri dish with colonies of those different types, microbial things growing, and several judges commented this was really creative. It was not creative to the point of being distracting and weird, which sometimes people get a little carried away. It was just right. It was very memorable and distinctive. So thank you, Cora, for. All right. So and the next category. Oh, sorry. My bad. No time. Okay.
Unless you want to do PowerPoint. We can do it later too.
Okay. So I just flashed up the next category. We had two students that did an exceptional job of team building, not only in sort of a friendship and connecting way among their peers, but also in the sense of using the group to give them data. So let's see, this was team building and crowdsourcing. The awards go to Prue and Susanna. And this is Prue on the day that she referenced in one of her figures, getting all the students to walk around campus with their smartphones, measuring those magnetic anomaly signals. And actually, when I saw this, I was like, isn't that what we all tend to look like nowadays? But, however, they were actually collecting scientific data, and it was a really fun day for everybody. So thanks to Prue for that, and then Susanna. I actually couldn't find a picture of her making everybody smile. Yeah, but here she is, going head to head with Joe in a team building exercise.
The girls pushed the boys in the paper rock scissors event, and they got really into it. It was great.
Yeah. So thank you so much to both Prue and Susanna for all your work, building our team even more strongly than it would have been without you.
And
you go. All right, thanks. Okay, the next category, as you may have gathered from the talks, there were a couple people who pioneered totally new methods and technology development this summer. And I think you might have to look at your memories for pictures of these guys setting up these large and intimidating looking machines, mass spectrometer, wind Doppler, LiDAR systems. But Mike and Davin had an unusual challenge in that they were doing a whole set of methods and techniques for the first time, and their mentors really recognized their hard work and how much effort it takes to do that. So we'd like to recognize them as the pioneers. Come on up. Hey, thanks, Mike. Congratulations. What happened to our low tech awards? I forgot the first one. Low tech. All right.
I'll give them out, I promise.
Okay, the next category, as you just saw, several students really had a ton of complex data to grapple with. Actually, almost all of you did, I would say. The ones that we thought did the most outstanding job deconstructing and kind of simplifying the take-home points from these data sets were James, Kelly, and Jason. And this is central to every scientist's life, and you guys, it was almost like you were thrown in at the deep end this summer with, thousands of data sets to work through. I think, didn't James say something about millions of lines of code?
Thousands.
Yeah, thousands.
Millions, a little up there.
Yeah. But anyway, please, let's recognize you for that. And I think also these three had excellent communication skills, showing that to the judges they could tell the story of that data.
You're next, we can do it.
All right, so our next category is endurance. We had two students who demonstrated exceptional endurance in all kinds of ways. These two both were the ones that battled up and down those big landslide areas that you may remember with carrying equipment. And then looking back, that seemed fun because one of their other phases of work was going through hundreds of images or more in their labs or offices and sort of processing what did those landslides look like on the screen or in the form of models. So we want to recognize Jess and Joe for their endurance. Great.
I'll give you later.
And the final award that we'd like to give is someone who had a little bit of a different study area. And Sean was our true field adventurer in this, and I was going to call this the Getting Wet and Dirty Award because I think you did almost all the getting wet part of the summer for all of us. So we wanted to recognize Sean, and also he had to be really patient because he was trying to spot the animals that he was studying, the wild beavers, and all he got was moose, 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 and more moose. So he's the only person to complain about that. But, exactly. But thank you, Sean, for sharing those adventures. Sean also took some great pictures when he was out in the field, and he showed me this one, and I really liked it. Can you explain this
impromptu go?
No, he said.
Okay, good.
Yeah, this was a very unfortunate beaver. The stump this was cut from is just off the camera frame here, and it fell perfectly to weave in between 5 separate aspen trees about here rib height on me, so you can see where the poor little guy tried desperately to get something of it and couldn't. So all of the work to cut down this tree was for naught.
But we also want to show an image that came to us from Joe. All of us.
I want to show this.
We really all appreciated Joe making us laugh with this natural slide. And so we have awards for you with that printed on too, because both the natural example and this really illustrated that our interns were very resilient. I have faith that one or more beavers will come back to that log in the woods and get it eventually. And I trust that this group of students would do the same. They would help each other out to overcome a challenge. And so I love the picture that Sean took in and this image that Joe shared because it sort of illustrated that resilient concept. And wherever everyone goes in their next steps of education and research and science and discovery and life, we would love you to remember RECCS as the time that you build those resilience skills. So thank you very much again, and we will be heading to enjoy some food and drinks now. Soon we will.
Oh,
Little she knows.
Super brightness.
My name is Andy too. We just want to say thank you for everything.
Oh, thanks so much. Wow, that was very
One more for Jenny, little does she know. So Jenny really helped us out this summer a lot with the science communication piece, and up beyond and above of what she was signed up to do maybe, but her passion for what working with RECCS students from her previous experience as a mentor was really eye-opening for me. I learned a lot from you, and I'm sure you guys did too. And so this is from the RECCS team, from the students and us. It's a big thank you for your help this summer.
Oh, thanks so much. Thank you, everybody. I already like this.